Now we had the group gamma, which was the image. So gamma for us, I want to think of gamma as a subgroup of PGL to QP, which was really, if you want, the image by eta of H Z 1 over P divided star divided by center, the image of that. And this is a discrete subgroup here. Inside, let's define lambda to be the group generated by this element S, by this set of P plus 1 elements set. So this is clearly inside gamma. But somehow we don't know what's the connection between it to gamma. At least this point we don't know. So we want to clarify this, and and here is the story. So claim, first of all, is that lambda is lambda acts transitively on the tree. P plus 1, you know, the tree associated with this y. Because this is an easy proof. That's something completely general. You have a group now you have a group acting on a tree. And you have elements inside the group which takes you to all the immediate neighbors. I claim that this already implies that you act transitively on the vertices, to be more precise, on the vertices of the tree. Why? Because we assume no element gamma in lambda satisfies, assume not. So assume not that it's not. So pick some y in the tree such that y is the closest possible to z point, you see, to the standard vertex. We have the standard vertex. And I'm taking, so this is the standard vertex, z0. I'm taking some y here, and this y is not in the orbit. And y is not in the orbit of lambda z0. Right? To prove that it acts transitively, I have to prove that the orbit of z0 is everything. Right? That's the meaning of acting transitively. So assume there is something which is zero. So in this case, I will look if I'm inside the tree. I have a path from. Actually, we don't even need a tree here. This is true for every path. This is a completely general lemma. Formulate it. So I have here z naught. I have a path going to y. I'll take the point here. I'll call it y prime. So let y prime be a vertex. So by the way, the distance between y to z naught is at least 2, right? Because we know that all the points of distance 1 are obtained, right? That's what we proved. So I take a vertex with distance of y prime to y is equal to 1, and distance between z naught to y prime is the distance between y to z naught minus 1. I have in the tree something which is one step closer. So by our assumption, therefore there exists some gamma lambda in lambda such that gamma acting on Z naught is equal Y prime. Right? But therefore, if I will look at gamma times S times Z naught, what is S of Z naught? Give me exactly the star around Z naught, right? That's what we said.
S times gamma.
No. No. Be careful. I really have to take Z naught, applying it on S.
You don't need gamma to move from.
No.
Why
No,
not?
just a second. No, it's important like that. That's, I used to be always confused also, that's why I can answer it quickly now. I did this mistake many times. So when I prepare the class, I check it. That's why. You see, you take Z naught, you move it by S to all the neighbors of Z naught. Now, what gamma does? Gamma takes Z naught. Gamma takes Z naught to Y prime, right? So gamma now will take the neighbors of Z naught to all the neighbors of Y prime, right? Because it preserves the combinatorial structure. One of these neighbors of gamma of Y prime is Y, because it has P plus 1 neighbors also. Are you all with me? Right? The star around, if Z naught is taking, if gamma is taking the point Z naught to Y prime, then gamma takes the star of Z naught, the immediate neighborhood, the kind of the sphere around Z naught, to the sphere around gamma prime. And Z naught contains Y, because Y is of distance 1. Or if you want, you can say gamma to the minus 1, Y, the distance of gamma to the minus 1, Y prime, and gamma to the minus 1, gamma to the minus 1, Y, is equal to the distance between Y prime to 1, maybe that's a nicer way to say it, which is equal to 1. Therefore, gamma to the minus 1 of Y is equal to alpha times Z naught, because this is Z naught. And if you are of distance 1, you are obtained from it. This means that alpha times gamma, it means that gamma alpha Z naught is equal to Y. So which means that we can get Y. It's a contradiction because we assume that Y is not obtained by an element. In fact, you even see that there is a unique such alpha. And from this uniqueness, we can deduce the second thing, which is that gamma is really a free group. Now, just be careful. Remark: if alpha in S, then alpha bar is also in S, because alpha. You remember what was S? S was set so that the first is odd and positive, right? Alpha bar, the first is still odd and positive. And alpha bar as an element, or let's say eta of alpha bar if you want, is f eta of alpha to the minus 1, you know. Or, in the group gamma, they are the inverse of each other. alpha times alpha bar is equal to alpha, which is equivalent, this is a number, times the identity, which is equivalent to the identity, which means that this is the inverse. So S equal to S to the minus 1 as a subset of lambda. And I claim now that lambda is a free group on S, but when S is the set and the generator. So it's a free group on P plus 1 over 2 generators. So the generators S, but these are the generators and their inverses. As a free group is a free group only on half of them. And this is basically the same proof, I could probably have to say together, because there is also this uniqueness. What's the best way to say it is that, what do you have to prove in order to prove that something is a free group?
It's a ping
You can do ping-pong, but first of, yeah, okay. You see, okay. I can give you several proofs. Let me give you an abstract proof, but then we'll see. If a group acts on a tree without there is no fixed point, then it is a free group. Why? Because we look at the tree modulo the action of the group, and by standard algebraic topology, the acting group is the fundamental domain, is the fundamental group of the quotient. The quotient is a graph, and a fundamental group of a graph is a free group. Okay? Now, how do I know, let's be careful here, how do I know that here there is no torsion? I claim that if there is a torsion, because the action is transitive, you see, then what is a torsion? A torsion are exactly stabilizers of element. If you act on a tree, if you have an element of finite order, then you take the orbit of it. The orbit of it is a finite set, and then the cyclic group preserving this finite set, and then it must preserve the, how you say, the center of gravity. Right? If you have a group acting on a finite set in a tree, it must have a fixed point, okay, or a fixed edge. Okay, do you see this?
Well, the center of
I will show you another proof in kind
center
of.
of gravity is not exactly defined, but you can define it.
You can define it, right? Which would be either an edge, either the middle of an edge.
Take a tree and you cut.
And you cut the edge. But that's kind of an abstract proof. But then you have to check that there is no element here which make a flip-flop, a flip-flop from an edge, which is true, but it should be checked.
Can you repeat what you just said?
What?
Can you repeat what you just said? I didn't get.
About center of gravity?
Yes, the whole thing.
Okay, so I will give you kind of two proofs.
It's not center of gravity, it's the center of the tree.
The
Center of the tree is what you obtain by repeatedly cutting the leaves. You cut the leaves.
You see, if assume you have a finite group acting on a tree, then there is always a fixed point,
Which is either a vertex or an edge.
which is either a vertex or an edge. Why? Because take an orbit, take one point, and take the orbit of it. The orbit of it is a finite set, which is preserved by your group. Take the convex all of this finite set. So take the minimal subtree containing this finite set.
Just cut
This-
off the rest.
Throw all the other. So this tree is preserved by your action. Now take the leaves of this tree, throw them away. So the middle one is also preserved. Take the leaves of that tree and throw it away. Then the middle point is.
So you get a blizzard.
And eventually you stay with either a vertex or an edge. Either you flip top to the edge or you preserve the edge. That's a standard lemma. Now, why? But how do I know that here I don't have a stabilizer of vertices. Here I can use the trick. I say all the elements that we worked with in S are inside the congruent subgroup mode 2. You remember this observation I made or I promised to make, right? That if we think of it, if we take a lambda inside the group H Z 1 over P, in this algebra first of all, there's elements in this algebra, then these elements are inside the kernel, so lambda is really inside the kernel from H Z 1 over P to H Z 1 over P modulo 2 H, modulo 2 Z 1 over P, which is simply H of F2. And this is in the kernel because the first element is odd and all the others are even. So I'm going to the identity. And therefore, all the product of them is also inside the congruent subgroup mode 2, and all the invertible elements are outside the congruent subgroup mode 2. And the elements which preserve the standard lattice are, you remember, are just plus minus 1, plus minus I, plus minus j, plus minus k. These are the only elements which preserve in and they are outside the congruent subgroup mode 2. So this is, if you want, kind of no, okay. And if you see, if a group acts transitively, and if then the stabilizers are all conjugate by that group, right? Because a stabilizer of one vertex is a conjugate of a stabilizer of another vertex if the group acts transitively. You see this, right? Because whatever it happens in this vertex is true also in the other vertex up to conjugation. So if there is no stabilizer for the standard lattice, there is no stabilizer to any other of the lattices. Okay, but this, I don't like this. I mean, I don't like the group. I want to convince you now in a kind of a concrete way that to show you that this is a free group by really, by working out, think about the previous proof. And I'll kind of show you that if there is, you see, if you take a point, let's see, we take a word in the generator S. A word in, I have alpha 1 up to alpha p plus 1. Okay, now, but just let's be careful. Here I have the generators and their inverses. I want to say that if I take a word in the generators and their inverses, such that this is a reduced word in the sense of free group. Everyone knows what I'm talking about, right? A reduced word, namely that I don't have an element and after that it's inverse. Okay? If this is a reduced word of length L, then I want to claim the W of alpha 1 up to alpha p plus 1 of Z naught star. This is a vertex whose distance from Z naught is exactly L. And in particular, this is a non-trivial element. And therefore, this is a free group. But it teaches me even more. Now, why this is true? Because, you see, think about this picture of what I showed you before. If you take the first p plus 1 elements, they take you to the immediate neighbors, right? Now you multiply each one of them by another element from S. So they take you from this vertex. Okay, sorry. I will multiply from the right. So, sorry. I will take, I say alpha took me here. Okay, I will prove it by induction. I think that will be better. I'll prove it by induction. So my word is alpha times W prime. And W prime is a reduced word. Okay? So W prime W prime took me from Z naught somewhere here. Sorry,
What are you doing?
not alpha, I want to say W prime times alpha. Let's say that W is equal to W prime times alpha. And alpha is in S. Okay?
You want to show the distance is L plus 1?
What?
The distance is L plus 1. What are you trying
Yeah. Okay, so I have to.
And alpha is not the end what? Not the W.
Should we take alpha from the other side?
No,
No, W is the
no, hold on.
Alpha is not the last
Just a second, I basically want to say that in the tree, each time when I come to some place, I have exactly one way to go backwards and P ways to go forward, right? The element which will take me backwards, okay, I know what element is going to take me backwards. Which element? If I arrived from here to here by multiplication by alpha, then if I will apply alpha to the minus 1, I will go backwards. That's it. In all other ways, I will go forward. So just do it from the beginning. You go, you apply alpha, you go further away from Z naught. If you want now, now you apply beta after you apply alpha. There is one way to go backwards and P ways to go forward. And we know what's the exact way to go backward, is by applying the last element you apply, the inverse of it. Then it will take you backward. In all other cases, you will go backward. Now do it, then you continue. You apply one way to go backward is only by canceling the previous step. If you don't cancel the previous step, you go forward, right? Which means that if there is never cancellation, then you go forward all the time in all these L steps. Okay? Is it okay or no? No, you're not happy. Ma?
It's absolutely okay.
What?
It's absolutely okay.
It's okay, absolutely. Right. So it's actually much simpler than all the previous. So right, we saw it. Okay, good. So this is a free group. Now, what does it mean? But I claim that we even see more than that it's a free group. In fact, we can identify in a very clear way, we can identify the conclusion of all this, that we have a beautiful identification. We can corollary the t plus 1 tree, this tree, the specific tree, can be identified. I mean, this what is tree, this B2 of F, can be identified with the Cayley graph of lambda with respect to the generators S. Why? This is clear. Because I associate Z naught is associated to the identity. The neighbors of identity are exactly the elements of S. The neighbors of the neighbors are multiplication of 2 elements. The neighbors of neighbor multiplication of 3 elements in all the reduced world. And that's exactly the tree. Right? The Cayley graph of this is indeed the P plus 1 regular tree. But it's not just an abstract isomorphism. I have now a very clear way of associating element from here to here. Okay. Now, let M equal 2 times Q. Q is any integer. And I will call it lambda m, if I will stress lambda 2q, will be the kernel from gamma. You remember gamma, this is this h z 1 over p star divided by center to h z 1 over p divided by the ideal 2 times m z 1 over p. I can take star also divided by its center. Namely, I'm defining now congruent subgroups.
Just
What?
Just
What?
just m, not 2.
2m.
If you divide by 2,
By m, sorry.
and q should be prime.
The 2q, okay.
And q should be prime.
No, not necessarily.
But
Yeah, in our paper we wrote q prime, but there is no
square free,
reason.
right?
What?
But you need square free also.
I need what?
Square free. Q is square free.
No.
Good.
No. This was a mistake we did in the paper to write it just for the
But then you have the Ramanujans.
No, it's nicer. You can write it nicer. I'll assume in a minute that Q is prime and also congruent to 1 mod 4 just for the beautiful of the exposition. But it's not really needed. Okay? So I have here, so this is a normal subgroup of gamma. So this is by definition, right? It's a kernel. Now this is a finite, right? This is a finite ring. If I take this ring divided by 2q, I'm getting basically, let's say that the m is, let's assume that q is prime to p. Okay? So I'm getting here a normal subgroup. This is a finite ring, right? And this is isomorphic to z modulo 2q. This is a finite ring. Invertible elements is a finite group. Divided by the center is a finite group. This is a normal subgroup of finite index. This is the so-called congruent subgroup mod 2q. And lambda 2q is really inside lambda, because our lambda is really inside lambda 2. In fact, it's equal to lambda 2, but I didn't check it. Sorry. No, that's not completely clear at this point. Well, okay, I have to say something here. Yeah, there's something to check here, maybe. Do I really care? No, I don't really care if it's really contained or not even. Even this is not clear. No, we don't even care about that. We'll see. I'll show you a little bit soft. I use soft method. In our paper, we use, because we wanted to know it for every Q, then we did something more precise. But today I will show you by soft method how we can get almost the required results. Okay? But what we should say, that we already know that lambda is a finite index subgroup. Why? Because if a group, now listen to that, if a group acts transitively, lambda is a discrete group because it's inside gamma, and it acts transitively on the vertices. If you act transitively on the vertices, you must be co-compact, right? Because we can identify the vertices. You remember that the vertices are equal to PGL2 QP divided by a maximal compact subgroup K. If lambda acts transitively on this, it really means that lambda times K is everything. That's really the meaning of acting transitively. That you can get every coset of K. These are the vertices. Remember that the vertices is equal to that. If you can go from K to every vertex, it means that by multiplication K by lambda, you're getting everything. And this is compact. So lambda is co-compact inside PGL, which means that it is a lattice in the sense of being co-compact in the Lie group. And therefore, and lambda is also a lattice. Therefore, it must be of finite index in, lambda must be of finite index in gamma. Okay? So that's we already know. In fact, I tell you it's equal to the congruence subgroup mod 2, if you really check, but that's not so crucial. Now, I want to say I want to compute the quotient graph. So now, if I want to compute the 3 divided by this group, which I call lambda 2q, this is the same as dividing the Cayley graph of gamma generated by S by this 2q, which is really the same as the Cayley graph of lambda divided by this 2q with respect to S. So, okay, I think it will be, okay, let's, believe me for that, I know that lambda is really exactly the lambda 2q. We can really follow that and check what's the index. You see, we are really left with something, a lambda is of index 8 inside gamma, because it's only the invertible elements which are missing, and you can check that they have the same index, and then you can identify them. But I don't want to stop for that because my time is almost over. And anyway, if you take Q sufficiently large, you will be inside. So anyway, let's assume that lambda is 2Q, and therefore this is really inside that. So there is no problem. We are really talking about the quotient. So this is really the Cayley graph of lambda divided by normal subgroup 2Q with respect to S. So now, if I want to compute this quotient, the big infinite tree divided by the action of these congruent subgroups in the arithmetic group, they are just Cayley graph of some finite group. This is a finite index subgroup inside this group. And I just have to identify to understand what is this finite group. And this, and I know that I'm going to get that the infinite tree divided by the infinite group is eventually just a finite graph and a very nice looking graph. It's a Cayley graph of some group. So you have to understand what is this group. Now this group is what? This is like, you see, if you have, let me take you to a case you are more familiar with. Like something like SL3, if you take SL, so if lambda is really gamma 2, is the congruent subgroup mod 2. Lambda 2, gamma 2. Then, if you divide congruent subgroup lambda 2 by congruent subgroup 2q, where q is also prime to 2, this is the same as, like say for SLM, if you take SLD, what is the if you take SLDZ, this is your gamma. And you take gamma 2, the congruent subgroup mod 2, divided by the congruent subgroup mod 2q. We know that gamma mod gamma 2q is SL2 of Z mod 2q. And by the Chinese reminder theorem, this is like SLD. This is SLD of Z mod 2 times SLD of Z mod Q. Right? But if you take the congruent subgroup mod Q, mod 2, you kill this stuff, and you start only with this. So here's the situation I now see that I'll have to rush it. I'll start next week from this very end, and I will repeat it, but I want now that you will get the full picture now, and then we'll complete the details next time. So this gamma 2, or lambda, this is for this gamma 4. In our case, we are really going to get this will be isomorphic like the like the quotient modulo Q. Now the quotient modulo Q of the full group, which means that this lambda 2 over lambda 2Q is going to be isomorphic to H of Z1 over P divided by Q star divided by the center. Now, assume, for simplicity really, the Q is congruent to 1 mod 4. So we have epsilon square root of minus 1 inside FQ. Now this is what? Z1 over P divided by Q is exactly H of FQ. Right? If I localize the ring and then divide by Q, this is the same as dividing Z by Q. Right? So this is the same as HFQ star divided by this center. But if epsilon minus 1 is in FQ, then, even if not, by the way, but let's see, then HFQ in a very explicit way is isomorphic to the 2 by 2 matrices over FQ. That's what we started today. That if the field contains the square root of minus 1, then the quaternion algebra splits over there, and we have an explicit splitting. And then, what is this? And then HFQ star is GL2FQ, and when you divide by the center, you're getting PGL2Q. So your group, well, we have to be a bit careful. This equality, I'm using here the so-called strong approximation theorem, which tells me that this map to this map is onto. For SLD, you know it. But you have to know it also for the quaternion algebra. Next time I will give you an argument that without the strong approximation will explain you why this is apple, at least if Q is large enough. That postpone it to next time. But what I want to say that all together, okay, now we have to be careful because that's not quite true. I can get there either PSL2 or PGL2. Sometimes I'm getting PSL and sometimes I'm getting PGL. And I will explain all this next time. So,
In the case here out, it's PGL.
no. There's a delicate point here. The question is whether P is a quadratic residue mod Q or not. I was a bit cheating here. I did it kind of too fast these last few minutes. I'll get back to that. Because the group is not similar to SLD, it's really similar to GLD. If you look at GLD of Z mod QZ, and you look by the center, that's not equal to GLD, GLD of Z mapped to GLD of FQ divided by the center is not always equal to PGLD. It's sometimes equal to PSL. I will analyze this. Okay? I was rushing a bit because to get in time. Okay, now, but what? Let me just say what we did today, and next time we will repeat these last 10 minutes of the talk, and we'll give more detail. We showed that we wanted to compute this infinite tree divided by some specific congruent subgroups of specific arithmetic group. Why we care? Because of a very general theorem saying that these quotients are always Ramanujan graphs. That's a story that we haven't touched at all, why this is true. But this is true. And now what we wanted is to compute them in a very explicit way. What we showed, that this infinite tree, in fact, you know, when we wrote our papers about the subject, we have a kind of a draft at the beginning that we said, okay, we have explicit example of Ramanujan graph, take this tree, divide by this group. And then we got telephone calls. At that time, there was no email. from computer scientists who said, okay, this is an explicit example, a construction in the mathematical sense, but not in the computer science sense. In the computer science sense, explicit construction means something that you can give a machine to do. Infinite tree divided by infinite group is not explicit. And this analysis is exactly to show that these quotients are so nice that they are really Cayley graph of specific finite groups. So I have to identify exactly the finite group. I have to identify the generators as element of that finite group, and that's what I will do last time. And then we will get a construction, a very explicit construction of Ramanujan graphs as Cayley graph of some defined finite groups.
The S, you can explicitly describe S inside the group.
Right.
But the element of S is from the Jacobi theorem. Are there explicit
No.
solutions? So
No.
this part you don't.
This one is not completely explicit. It's explicit in the sense that you have to solve all the data. But from the computer science point of view, for most applications, when they want explicit example, the P is fixed. For computing from Jacobi theorem for P fixed is a constant problem from their point of view. But if P is going to infinity, that's if you really care about that, then that's a real issue. In some sense, in the higher dimensional, I think maybe situation is better. Now that's what we'll do. And all this is for dimension 2. The situation for dimension D is infinitely more complicated.
Or dimension 1.
Oh well, dimension 1, but I mean like PGL2. And then I think you will hate me if I'll show you all the details in the dimension D, but I will tell you the story as a story how to continue to dimension D and to get Ramanujan complexes, and still without giving you the why they are Ramanujan, which then we'll decide which to take. But as you can see, there is a lot of things to do, but I hope you get a flavor. I'm sorry I was not so well organized today.